What are the odds that a mammal, a fish, and a reptile would all independently invent the same body? Not similar. The exact same body, down to the crescent-shaped tail, streamlined torso, pointed snout, and dark back over pale belly. Dolphins have it. Sharks have had it for over 400 million years. And ichthyosaurs, a group of marine reptiles that went extinct before the first dolphin ancestor even existed, had it too. These three lineages never met, never shared genes, never had a common ancestor that looked anything like them. Yet the ocean turned all three into the same torpedo. If you'd ask a biologist in mid-2050 to compare these three animals, they would have told you the similarities were superficial. A shark is a cartilaginous fish that breathes through gills, you see. A dolphin is a warm-blooded mammal that nurses its young and breathes air. An ichthyosaur was a marine reptile that gave live birth in open water and vanished roughly 90 million years ago. Million years before the asteroid that killed the dinosaurs. Three separate branches of the vertebrate family tree, separate by hundreds of millions of years of evolution. And yet, if you line up their silhouettes, the outlines are nearly identical. The explanation comes down to physics. Water is roughly 800 times denser than air, and moving through it at speed creates enormous drag. Any animal that needs to swim fast and far faces the same engineering problem. Reduce drag at the front, smooth turbulence along the flanks, and drive thrust cleanly from the tail. There is only one shape that solves all three problems simultaneously. It is called the fusiform body plan, a tapered cylinder with a narrow tail stalk and a crescent-shaped caudal fin. Engineers figured this out when they started designing submarines and torpedoes. Evolution figured it out at least three separate times, hundreds of millions of years apart. Sharks were first. The earliest shark-like fossils date back roughly 450 million years, according to the Natural History Museum in London. Those early sharks looked nothing like the streamlined predators swimming today. They were slow, bottom-dwelling, and strange. Modern lineage sharks, the group that includes great whites and macos, didn't evolve their fully fusiform shape until around 200 million years ago. According to a 2004 study published in Nature by Bernal and colleagues, lineage sharks and tunas independently evolved nearly identical adaptations for high-speed cruising, including a streamlined torpedo profile, a lunate tail, and regional endothermy, ability to keep parts of the body warmer than the surrounding water. The ichthyosaurs came next. They appeared roughly 250 million years ago, according to Britannica, starting as small, lizard-like animals that waded into shallow seas. Within about 50 million years, they had transformed into some of the fastest marine predators the planet had ever seen. Their bodies became smooth and hydrodynamic. Their limbs flattened into steering paddles. Their tails grew vertical crescent fins, powered by undulating the entire rear half of the body. By the late Triassic, a large ichthyosaur in profile was almost indistinguishable from a modern dolphin. Then the color pattern. A team led by Johan Lindgren published a study in Nature that found preserved melanin pigments in ichthyosaur skin fossils. According to Lindgren's team, the pigment distribution showed dark coloring on the dorsal surface and lighter coloring on the ventral surface. Dark on top, light on the bottom, countershading. The same camouflage strategy used by sharks, dolphins, penguins, and dozens of other marine animals. It works because sunlight comes from above. A dark back blends with the deep water when seen from above, and a light belly blends with the bright surface when seen from below. Ichthyosaurs arrived at this solution independently, millions of years before any dolphin existed. Dolphins were the last to join the torpedo club. The cetacean lineage, the group that includes all whales and dolphins, traces back roughly 50 million years to small, four-legged mammals that waded into rivers and estuaries. According to researchers studying cetacean evolution, the earliest ancestors looked something like a dog-sized wading animal. Over tens of millions of years, the hind legs shrank and disappeared. The front limbs became flippers. The nostrils migrated to the top of the skull, and the tail broadened into a horizontal fluke. Modern dolphins in the family Delphinidae appeared roughly 12 to 15 million years ago. By that point, The torpedo shape was complete, matching a body plan that sharks had been wearing for over 100 million years and ichthyosaurs had abandoned 90 million years earlier. The swimming mechanics converged too. Biologists classify swimming styles by which part of the body generates thrust. The highest performance category is called tuniform locomotion, named after tunas. In tuniform swimming, the body stays mostly rigid while the tail beats rapidly back and forth. This style minimizes drag by keeping the wide body stable and concentrating all propulsive movement in the narrow tail stalk and crescent fin. Lineage sharks swim this way. Tunas swim this way. Dolphins swim this way. Ichthyosaurs, based on their skeletal anatomy and tail structure, almost certainly swim this way too. 4 lineages, 1 solution. Confabis study, published by the Royal Society, examined the hydrodynamic principles behind this convergence in detail. According to the paper, the relationship between body shape and drag reduction in aquatic vertebrates follows predictable physical constraints. A fusiform body with a fineness ratio between about 4 and 7 to 1, meaning 4-7 times longer than it is wide, produces the lowest drag coefficient at cruising speeds. Go wider and pressure drag increases. Go narrower and friction drag from surface area takes over. The sweet spot is a narrow band, and sharks, ichthyosaurs, tunas, and dolphins all landed in it. If you're finding this interesting, hit subscribe. More deep dives into animal evolution come out on this channel regularly. The tail shapes converge for similar reasons. A crescent-shaped or lunate tail generates thrust more efficiently than a broad fan-shaped tail because it minimizes the amount of energy lost to vortices at the fin tips. Airplane wings work on the same principle. High aspect ratio wings, long and narrow, are more fuel efficient than short, stubby ones. The crescent tail is the aquatic equivalent. Lineage sharks and tunas both evolved a heat exchange system in their blood vessels called a reed mirabile, a wonderful net of arteries and veins packed tightly together so that warm blood flowing out from the muscles heats cool blood flowing in from the gills. This lets them keep their swimming muscles, eyes, and brain significantly warmer than the ocean around them. Warmer muscles contract faster, which means faster swimming. Dolphins, being mammals, are already warm-blooded. They solved the same problem through a completely different evolutionary path, inheriting endothermy from their land-dwelling ancestors. 3 groups, 3 different mechanisms, 1 functional outcome: warm muscles powering a torpedo through cold water. The skull tells a convergent story too. All 3 groups evolved elongated, pointed rostrums, the bony snout that slices through water at the leading edge. In dolphins, the rostrum is formed from the premaxillary and maxillary bones. In ichthyosaurs, from different skull bones rearranged into the same shape. In sharks, from cartilage rather than bone entirely. The materials differ, the construction differs. The result is the same pointed wedge. Even the eye placement converged. Large, forward-oriented eyes sit on either side of a narrow head, giving both binocular overlap for judging distance to prey and a wide peripheral field for detecting threats. Ichthyosaurs had some of the largest eyes relative to body size of any vertebrate ever measured, suggesting they hunted in deep or murky water, where gathering every photon mattered. Biologists have a name for all of this: convergent evolution. When unrelated organisms independently evolve similar traits because they face similar environmental pressures. But the torpedo body plan is one of the most striking examples in the entire fossil record because the convergence is so thorough. It is not just one trait, it is the whole package. Shape, color, tail, swimming style, body proportions, skull geometry, even aspects of internal temperature regulation, all arriving at the same answers in animals that have no business looking alike. The reason is that water does not negotiate. It imposes physical constraints that are the same whether you are a Jurassic reptile, a Paleozoic fish, or a mammal that walked back into the ocean 50 million years ago. Drag is drag, thrust is thrust. The math does not change because your ancestry does. And when the math has a single optimal solution, evolution finds it, over and over again, separated by hundreds of millions of years and zero genetic connection. Somewhere in the open ocean right now, a mako shark is cruising at speed, and its body outline would overlay perfectly onto an ichthyosaur that died before flowers existed, and onto a dolphin whose ancestors were once chasing rodents on dry land. 3 lineages arrived at the same answer to the same question. If you want more stories like this, they are all on the channel.